Hello everyone. So today we are talking about disjoint set data structure. There's another name by which it is called. It's called union find data structure. Okay. Now we will talk about this data structure as an abstract data type first. So this may be a new concept. So I'll try to explain what do I mean by an abstract data type, and then we will go to the implementation part. So implementation so that it is efficient for my algorithm. Okay. So now let me first talk about this abstract data type concept. So normally when you will see, so what do we mean by a data type or data structure? So whenever we write a program, what we generally do, we specify a particular data type. So I can talk about say integer, or I can talk about my user defined data type. Such that it helps in my algorithm. It helps in my algorithm. Okay. But in certain cases, the actual data type, I mean, how are you actually implementing it and all, it may not be very, very important for the design of the algorithm. So in some cases, actual data type is not so important. So then what is important? Let's take an example. So for example, suppose you are writing an algorithm, and for your algorithm you need a queue, that is a first in first out queue of items. So what do we mean by that? You need to be able to do certain operations. So I need certain operations. Now what are the examples? So for example, in a queue you want, okay, I want to insert items in the queue, and I want to remove items from the queue. Following this first in first out principle, and there may be other operations like, okay, finding out is the queue empty, and so on. So now from a person who is actually writing an algorithm, okay, so it is convenient that we agree, okay, by this FIFOQ data type, I need these operations. So it's convenient that we agree on the operations without specifying what is my data type of the items. And assuming that I can use these operations, I design my algorithm. So then what I'm doing actually, so the ADT that will satisfy or that will support these operations is FIFOQ. So this is an abstract data type that supports these operations. So now, so you see what I have done now. So till now, whenever we try to implement a data structure, we always go to when we try to define a data structure. So generally what we have done till now, we will immediately talk about, okay, just the implementation view. But now what we are saying, okay, it's not the only view. So we are saying this is not the only view. So you can think of a data structure from an operational view. So what are the operations defined on this? So for example, if I have first out queue, I will have operations like insert, remove, and so on. Now I have an operational view, and this operational view can be implemented in various ways. And there is an implementation view. So I can implement these operations in many ways. For example, for queue, you would have seen at least two ways of implementing a queue. You can use arrays for implementing, or you can use linked list for implementing. But the idea is that if you define these two views clearly, then the user of the data structure does not need to bother about the implementation view. So how will that help? Now I am saying by using an operational view, I am defining a very general abstract, that's why it's called abstracts. So abstract data type. And that may not be specific to a particular problem that I am solving. So it becomes more general. Okay. So yeah, examples of where you can see ADT are queue. Similarly, you can see another example is stack. Similarly, so there are certain operations. I should be able to push an element, or I should be able to pop an element. So I will need to define certain operations. But then there is another view of implementation, and I can do implementation using either arrays or linked list or maybe something else. Okay, but as a user, you just need to know the operational view and say, okay, I can use this ADT, and if I use the ADT, I will get all these operations. So then whenever I am designing an algorithm, so while designing an algorithm, what you will do, so if you see that, if you realize that your needs correspond to a particular abstract data type, then you immediately use that. And because the implementation is separate, the implementation is independent of your particular problem that you are solving, so this helps in making a much more modular process. So you have an ADT defined, and you have an algo. So with ADT, you know what are the operations, and with your algo, you are directly using the ADT, and without worrying about implementation details. Although, as we will see, we cannot always ignore this. Okay, so the caution is that we cannot always ignore these, that we will also see today itself. Okay. So now this is a generic idea about ADT, abstract data type. So whenever you are talked about abstract data type, you will immediately say, okay, I need to think about the operations. What are the operations I need to define? And once I have the operations, I list down the operations. So list down the operations. And then there can be suitable implementations, multiple suitable implementations. Okay. Now with this context, now let's talk about our disjoint set or union find as an abstract data type. Okay. And this is actually a very nice example of, it's not so straightforward data structure. So it's a nice example of not so straightforward data structure. That helps in improving the efficiency of the algorithms. Okay, so now let me define the setting. Where exactly are we using this disjoint set data structure? So what is the setting? So in the setting there are n elements. Suppose these are x1 up to xn. Okay, and assume they are divided into disjoint sets. Okay. Now in the setting, initially each element is a group in itself. Okay. But now there are certain operations that you are defining for this. What are the operations that you are defining? So there are three operations with this disjoint set data structure. So one is make set. So given an element x, it creates a singleton set containing that element. Okay, and it gives some ID to that. So ID can be x itself or something. Second operation is find set. So you are given the element x, you have to find the ID of the set it belongs to. Okay. And then there is another operation like union xy. So that is, you create a single set of two sets containing x and y. So there is one set that contains x, another set that contains y, and you create a single set out of these two sets. And this new set can have ID of any of these. Okay. Now these are the three operations, and any And this abstract data type that is supporting these three operations is called the disjoint set data structure. Now, where actually you will need this? What kind of algorithms you will need this? So example of an algo. So you will actually see an algo when you will see the spanning tree algorithms. So minimum spanning tree, and you will see Kruskal's algorithm that requires this. But yeah, I'm not going into that because it will be covered anyway. So I will give you another algorithm where you need this sort of data structure or abstract data type. So what is the setting of my algorithm? So suppose you are given a social network. So think of a social network. So example can be Facebook or anything. It can be Twitter or whatever. It can be an actual network depending on whether people are staying together in the same hall or so, right? So this can be a social network. Now, and the social network is defined by a set of people, so V, and a set of edges that define a relationship between pair of people. Say E. Okay, and these are given in no particular order. So for example, you can think of all your class. So yeah, roll number 1, roll number 2, or whatever. And you are given V is the set of all roll numbers. And then there are what is E. So this is V. And in E you are given, which 2 roll numbers are connected in a social network. Say R2, R3 are friends in Facebook, R5, R10 are friends in Facebook, and so on. Right? So you are given only this information, what is V and what are E, and they are given in no particular order. No, they are not sorted or anything. They are just told, all these people have connections. Now in a social network, how will that look like? So you will have thing like, there will be some roll numbers R1 and R2, they are connected. Some R10 is connected to both of them. Then say R10 is connected to R20 and R20 is connected to some R37. Similarly, there can be another 2 people like R100 and R105, they are connected, and so on. So you see, in terms of graph, you can immediately see there are some. This is a single connected component, and this is another connected component. Okay. Now suppose you want to write an algorithm. So write an algorithm that finds out all the connected components. First of all, and then for each person can tell, which component it belongs to. And for each person, X and V, it outputs the connected component it belongs to. So you may have some names for each. This can be component 1, this can be component 5, and so on. So if you give an input, like if the algorithm should be able to tell, okay, R2 belongs to C1, R100 belongs to C5, and so on. So that is what your output should be. Now, you can't make any assumptions about the ordering of E. Otherwise, you could have used some algorithm that is inspired from the traversal algorithms. Okay. Otherwise, traversal algorithms could be used. And suppose you get to scan E only once. So think of the case where E is really large and you cannot store it, but you can scan through this once. Okay. So in that case, what kind of data, what kind of algorithm you can use? Okay. So now we are, so if I'm thinking of an algorithm, so what would be an algorithm in this case? And because we have defined the data type, you will think of an algorithm that uses my ADT. Okay, so let's try to define an algorithm. Actually, it looks very easy, right? You have people, you have people, you have people, and you have edges. Okay, so what you should ideally do, firstly, put all the person in separate sets, separate disjoint sets, and now you traverse or scan through edges one by one, and whenever you find two people connected, you say, okay, go back and check if they belong to different sets. If they belong to different set, take a union of this, and that's all. And at some point it may happen that you can, so once you finish, the people who are connected together will be in the same set. They will have the same ID. And this looks quite easy in terms of algorithm. So you can say, for each x in V, do make set x. Then for each xy in capital E, do. So you first find out if they are in the same set or not. If find x is not equal to find y, then you do union xy. And that's all. And finally, for each x in V, you output this person x belongs to what is the set or component find x. That's all. So what does this algorithm uses? So what does this algorithm uses? It uses the three operations we had defined: make set, find, and union. Okay, and how many of these? So suppose there are m edges and n people. So it uses find m times. It's actually 2m times, because for each edge it is finding for both the persons. So it's 2m times find, and if find x is same as or not same as find y, they will do union. So how many times it is doing union? Is it doing union m times? So this we can think of it. So you see, whenever you do a union, two sets merge into a single set. Okay, so you cannot do a union more than the number of sets involved, because find x needs to be different from find y. So the maximum number of times you can do union xy is the number of sets, minus 1. So it is n people here, so at most n, let's say n times. So you can do maximum n union. Okay. So in general, something like I can say, okay, some order m find operation in order n union operation. This is all I need to do. And if you think of the make set, so then you also have order n times make set. So this is what you will need. So now once we have seen the algorithm, when we know what are the operations, then we can see, okay, how will I be implementing this ADT? How will I be implementing this ADT? So that, let's also keep in mind, so that my algorithm is faster. Okay. But the ADT principle is that now you can, so actually once you have defined this algorithm, you are as if you're calling some prototypes, make set, union, and find. So ideally you can implement the union find data structure in any way and use here. But you also want efficiency. So we will see what are the ways you can implement it and which one is efficient for this particular scenario and which one is not so efficient. So now let's look at the implementation view. So what is the simplest way you can think about implementing this disjoint set data structure? So what is the simplest implementation? Can I do it using a static array? Because I know there are n people. So can I use an array? So use an array. X okay, so I have 1 to n, so they are denoted by 0 to n minus 1, and the ith index, what should I store? See, remember, what do I need? I need make set, I need find, I need union. So a very crucial operation is find. So I need to find what is the set to which component to which element I belongs. So what I can do in this, so xi stores the identity of the group that contains element I, the ith element. So I can simply store the identity of the group in each of the element of this array, and this find x is an order 1 operation then. It's a constant time operation. Simply look at the array. The index of the array. Okay. So find x is easy. Make set is anyway very, very easy. So I can define some initially for make set I can just define a group ID to each element. It can be as simple as the element itself. So suppose I have elements such 3, 7, 11, 12. So I can initially start with the ID as 3, 7, 11 and 12 at the 4 indices of the array. And find x would be easy. If I know find for ith element, I simply look at the index and say what is the ID of that element. But then now I have to do union. So union, what do I mean by union? So I had this 3, 7, 11, 12. Now suppose I am told that 3 and 7 are part of the same group. So initially it was 3, 7, 11 and 12. Now they are part of the same group. That means I need to do a union of these. And what do I do in union xy? I need to put the ID of both the sets same. You can use one of the IDs. So let's say I use ID of 3. So then what would happen? I'll have 3. So even for the other set, I'll make the ID as 3. 11, 12. Now you see there are 3 components. One with ID 3, another with ID 11, another with ID 12. 3 components as a result of union. And I can still do find. I can find what is for find of 7. You know what is the index of 7, and then you see, okay, this is 3. So now what will be the complexity of this union? So what you're doing in union? Change. So if you're doing union AB, the identity of, now you have to change not only for Y, but all the elements that belong to the set to which Y belongs to. Each element in B to A. Well, what is B? B is the set containing Y, and A is the set containing X. Okay. So yeah, so let's say there you know the sets already. A is the set containing X, B is the set containing Y. Now if you are doing union, you are putting ID of each element of B to A. So B can have B1 to Bn or whatever Bn, and you make each of these IDs as that of A. Let's say A was the ID. So what is the complexity of this operation? In the worst case, the two sets we are merging are order n, right? In the worst case. And then you will have to change identity of nearly order n elements. So it can be worst case order n complexity. Okay, and if that is the case, then what will be your complexity of, say, M find and N union? So M find will be fine, it's M, this is order M, but N union will become order N square. So this will become order M plus N square. So this is what you can get in a simple array-based implementation, and it's not very efficient. And then the question is, can I do better than this? So can I go beyond arrays to some other data structure? So what are data structure that comes to your mind? Sure. So the next data structure we can think of is a linked list. So can we use a linked list data structure? So what I will have to do? So I can't think of a single linked list, but let us say, so each set is denoted by a linked list. Okay. So how will this look like? So you have, so how will you create a set? So you have a head, and this points to the first element. and that points to null. Okay. So this is a singleton set. Now, okay. So now you will say, okay, fine. How will I know? So there, I have not given details of what do I need to store, but what do I need? I at least need the ID of this set. So I can store the ID inside head. But since I'm only using one pointer, how will I know the ID of this element? So how would I reach the head from this element? Because in general, I have to think the general case. General case would have a head and it would have multiple such elements. So how would I, given an element here, how would I reach head? And I want to do that efficiently. Well, you will say now I have already shown. Why don't I do that? Why don't I have a back pointer that directly points to the head? Okay, so that sounds nice. So I can have a pointer that will point to the head. Yes, and the data and next pointer. Sure. Data is stored here and there's a next pointer. So that means each element I am containing a back pointer and a next pointer and the data. Now what should the head store? It should store the ID. So what is the ID? Show the ID, right? And actually it does not even need this. So in your implementation, you can define a separate type of node for head, or yeah, or you can keep this pointer to null. So whatever. So this is how your linked list for a single set look like. And by using the back pointers, how will that help? I can do find x very, uh, find x will be order one. I directly go to the head of this linked list. Okay. What about make set? Make set is nothing but creating this thing, and this is a constant number of uh, creations, right? Some pointers and some nodes. So make set is also order one. So let me just write that again. So you have a back pointer and the head node stores the ID of the set. So fine, your find x was order one now, and make set is order one. They were anyway order one in the array that you were trying. So what about the union xy? So union xy, what you will need to do? So you are having two lists. Let's say these are the two lists. And you have to do a union of these. So, and that has to point to one of the two heads. So let's say I want to do a union and I want to point to this. I want to make this as the head. So what will you need to do? So you will need to add one list to the tail of another. Sure. So that means in general, that also tells you should have the head and tail pointers of each list. Okay. So you have that. Now you want to put one list to the, you want to add one list to the tail of another. So something like break from here and put it so, or in other words, this pointer is now pointing to here. Okay, so this will be your new list. And yeah, this is not as simple as that. This is just a single pointer change, but then all the back pointers, this, because this was earlier pointing to here, here, while this was pointing to here, now you will have to change this. So this will now go from here to here, and this will now go here. Okay. So that means what I have to do, so add one list to the tail of another is a single pointer update, but you have to change back pointers. So say suppose one list A to the tail of another, say B, so back pointers of all the nodes in list A. So you will need to do that. Now immediately you see, okay, this looks as bad as the array-based implementation, because now this, in the worst case, this can be again order n, and you are doing it, you are doing union xy n times, so this will again lead to order m plus n square sort of thing. So yeah, we tried a complicated structure, array which was so simple, so this was a more complicated, but this is again inefficient. So now immediately I will ask, okay, can I do better than this? So I'm using linked list. Can I do better than this? So can we do better? So now you'll go back and check that yes, the two lists that you are adding, you're adding one list to the another, the sizes may be different. So this had a size of 2 and this had a size of 1. Now whatever list I'm adding to the tail of another, so if I'm adding A to the tail of B, I have to change back pointers for all the elements of it, right? So if the two lists are of different size, it makes sense to add the smaller list to the tail of larger list. And I can do that simply if I store the number of elements in each list in the head element. So what I need to do better? So first keep number of nodes in each list, same head, and then during union add the smaller list to the end of larger list. Okay, but yeah, doing that, will that overall, will that help? Because you see, I can make an argument in the worst case, the smaller list can also be n by 2. Right? And then even if you're adding n by 2 elements, you're changing. So that means changing n by 2 back pointers. So how will that be better? So yeah, the answer lies in that yes. So if you think about the worst case here, this will not show that this is doing better. But let's look at how many changes we are doing. Okay, so let's actually look at. So let's do a bit more deep analysis at the number of changes we are doing. Okay. So look at any node. Okay, so what we will do, so look at a node, just find out overall how many times you will update its back pointer. So find an upper bound on the total number of times its back pointer is updated. Okay, let's try that. So what I'm ensuring, so you add a, so suppose take this node. Okay, it could have been in many lists throughout its journey, starting from a singleton list. Okay, so I change its back pointer when it is appended at the end of a larger list. Right. So think about the first time. So the first time its back pointer was updated. What would have been the size of the resultant linked list? It, because it would be added to a larger one, so it will be at least 2. Can be same. Yes, cannot be smaller. So it was added to a linked list of size 1, so it would be at least 2. Okay. Now you see the second time. Its back pointer was changed. So what will be the size of the resultant linked list? Because it would have been already size 2 by the first update. So the resultant should be at least 4. And like that you count. Okay. So third time it will be 8, right? And you will see you will go into the power of 2. So if it is updated t times or k times, kth time, it will be 2 to the power k. But finally, this has a limit. It cannot be more than n. There are n elements only. So max, so kh order log n. So for a single node, you can update its back pointer at most order log n time. And that gives a huge relief immediately. So for a single node, you can do at most order log n updates. So that means for your n nodes, you can do at most order n log n updates. And that means, okay, the complexity of m find plus n union would be O m plus n log n. And that becomes better than by linked list, and that becomes better than O m plus n square by a static array. Okay. Now, yeah, what was this analysis that we did? So you see, in the worst case for each node you are, so in the worst case, let's look at each operation. So for each operation, what do I mean by an operation? That is adding a list to the tail of another list. So in the worst case, an operation can take order n time. Yes. But when you look at the series of operations, so each operation will not be order n. Okay, so why don't I do an analysis over a series of operations? So if I look at, so in general, what I'm doing, so in a series of operations, so what might happen, the worst case complexity for any of the operation may be high. Any one operation may be high. But if you see on an average, this complexity may be low. And looking at this, so looking at this average over a sequence, this gives a more reasonable estimate. Because you know that you are doing an operation for a certain sequence, right? So it's better to look at an average over a sequence. So this sort of analysis is called an amortized analysis. So where you do not look at independently each operation and say, okay, independently, if I look at independently, there may be a worst case. Worst case may be high. But if you look at a sequence of operations, and then do an average analysis. Like here we said, okay, for a node, let's do an average analysis, how many times its back pointer will be updated, and do it for all the nodes. And that gave us, in this case, so amortized analysis gives us for a node order log n amortized time complexity for back pointer update. And this tells you, okay, overall I have order and log n, time complexity for this. So this was again very interesting, this linked list and the analysis, and this gives me slightly better than a linear array. Now can I try out some other data structure also for this particular task? So there is another very popular implementation, and this is via rooted trees. Okay. So what do we do here? So in this implementation, so each set that you're considering is a rooted tree. This also can be shown as an inverted tree. Okay. And ID of a set is nothing but ID of root. Okay. So it will look something like this. So suppose I have three, so I'm showing three sets. So it can be, say one is the root, it's inverted tree, okay? And it will have only parent pointer, 4 and 7. And one is the root, and 1 points to itself. Similarly, 2 points to itself, 2 is the root, then 3 and 6 point to 2, and 9 points to 6. And similarly, 5, 10, 8, 11, 12. This is another set. So I'm denoting three sets here. So what you're seeing here, so each node stores the element, what is the key of the set, and a parent pointer. To the parent node. Okay, and the root will points to the parent pointer of the root points to itself. Okay, now fine. So how will I do the three operations here? So make set X is easy. So I will simply create a tree with X as the node and its parent pointer to itself. Okay. So this is your make set. And this will simply take order. X itself will be the ID. It can take order one time. Now, what about find set X? No, when you think about find set X, that's where the parent pointers will be helpful. For example, look at this particular tree. And I want to do find set for, or let's say this one, find set for 11. Say find set for 11. So what will I have to do? I know where is 11. So this is one assumption we will have to make, that in all the data structure we are implementing, we have an order one way to access this. So something like I can store it a priori somewhere. What is the address of 11 in my data structure? So I have access to 11, and now given 11, I want to find the set it belongs to, and that I can do by following the parent pointers. So follow the parent pointers up to a point where the parent pointer comes back to itself. Okay, that time I know, okay, I have reached the root. And I say, okay, 5 is the parent of, so find set 11 should return me 5. Okay, the root of the tree in which to which 11 belongs. So what I do in find set, you simply follow parent pointers to the root. Now what will I do now in the third operation, that is union of x and y. Okay, so the only thing you will do, you will take, so you say think about these two trees, this and this, and you want to do a union of this. What is the easiest way? The easiest way would be, okay, I take the root of one of the trees, say this one, and point it to the root of another tree directly. So I just make this change. So this one, instead of pointing to itself, it starts pointing to 1. And this would be sufficient because now you can see uh, all the elements in this set now point to 1. You see 9, 6 to 2, and 2 points to 1, and 1 points to itself, so 1 becomes the root. So now everything for all the elements in these two sets, 1 becomes the ID for finds. So union is very easy for any two elements where root, one of the root becomes the child of another root. So you hang root of one tree, a child of another. Okay. So yeah, how much time they will take. So as such, in union xy, if before doing union xy you already have the set IDs, so if you have the set IDs, because generally in the algorithms how we call it is, uh, I already have got their IDs in find set, then it is an order 1 operation. It's an order 1 operation. You have the set IDs and then you simply uh, take the root of one of this to another. But what about find set? So here you have to follow the path, okay? And in the worst case, because I have no guarantee about the tree being balanced, so in the worst case, this can be order n. Now, this is bad. This is bad because you have to do m operations and this will give a complexity of order mn plus n, right? And this is bad, not efficient. Now can we do better than this? Can we do better than this? So can I use the idea that I was using for the linked list? So can I do better? Or can I do something to balance the trees? So remember what was the idea that helped me in the linked list? That when you are in the case of linked list, when you are adding adding a tree, adding a set A to the tail of set B, make sure that set A is smaller. Okay. Similarly, can I do something for balancing? So you see, what do I do? I have two trees. And in doing union, I take the pointer of one of the tree and put to another. So I can either do this or I can do this. So I can do either one or two. Now which one would lead to a more balanced tree? You see, earlier the height was 2. If I follow 1 and this height was 1, follow 1 my height will be 2, because the height of the tree that is being made, the set overall is not changing. Height of this tree is not changing. Only the height of another tree for which we are connecting the root to this tree is changing. And this will increase by 1. This will increase by 1. And so overall height will remain 2. But if I follow 2, because the height of this tree will change, it will increase by 1, my height will become 3. So that means what makes sense? So when a union is performed, the pointer of the smaller group is set to point to the root of the larger group. Okay. So that is what we can see intuitively. But can I also prove something about the height being order log n if I do this? Okay. So if we use this balancing, any tree of height h must have at least 2 to the power h elements. Okay, and this is something we can prove. And prove what kind of technique we can use. So actually we can prove using induction. So base case, you have a tree with say height 1. So, and there are 2 elements at least. Yes. So this is fine. Now think about the union now. So when I am doing union, I am taking 2 sets A and B, and let's assume that without loss of generality, let us say A is larger among the 2. So then, my resultant tree will have a height of max HA or HB plus 1. Because what I will do, I'll put root of the smaller tree and hang it onto A. So A's height is not increasing, but the resultant tree would be either max of HA and HB plus 1. Okay. Now this is the induction step, and we assume that the induction step, and by strong induction I assume that both A and B, so that is both trees, they follow the property, that is if the height is HA, then it has greater than equal to 2 to the power HA children, and this has greater than equal to 2 to the power HB children. Okay. Now I have to prove that the resultant tree will continue to follow this property. So that is actually very easy. So there can be two cases. So case 1 could be, so you have H is max of HA and HB plus 1. So case 1 would be HA is larger among the two. Okay. So then, and yeah, you're calling the final set as A. So the final set, so you can see its height remains the same, has the same height as that of A, but what can you say now? It has more elements, because now all the elements from B are attached to it. Now A was already following this, so, and that means, so HA was already greater than equal to 2 to the power, sorry, the number of elements in A was already greater than 2 to the power HA. So then you can say number of elements in, it's a new set, will be greater than equal to NA, which is greater than equal to 2 to the power HA, right, and that is same as 2 to the power H of the new set. So that means yes, overall it follows this property. Fine. Now what would be case 2? That HB plus 1 is larger among the two. Okay, if that happens, then what can you say? Now HB was already following the property, so NB was greater than equal to 2 to the power HB. Now N new, what can you say about the number of elements in the new set? Because now B was the shorter one, so the new tree will have at least twice the elements, 2 times NB. Okay, so if it has at least twice the elements, then, so this is equal to 2 to the power HB plus 1 greater than equal to, and that is same as 2 to the power H new. So again same thing, so that means in either of the case, new tree will contain at least 2 to the power H elements. Okay, so here one word of caution, that when we are taking the decision of which set to move to another set, we take it by the group size. So by the set size. So the smaller group is set to point to the root of larger group. So here, when I was saying why the new set will have at least 2 times NB, because B was the smaller set. Right? So that's why it will have at least 2 NB, and the rest of the things are easy. So in both the cases, the new tree will contain at least 2 to the power h elements, and this is the proof. Okay. So that is very good. So now what I am saying, if we use balancing, so using balancing, I can ensure trees have at least 2 to the power h elements, or size is log n for n elements. So that means the find operation can now be done in O log n time, and that gives the overall complexity of n plus m log n. Okay, sure, fine. That looks reasonably close to what I had in the linked list. So that is quite similar. No, but then why? What was the need of using this data structure? So the idea is that you can actually do better than this. So we can actually do better than this. How? So there is a nice idea that we haven't used till now, and this is called a path compression. So the idea is path compression. What is this idea? So the idea is that you see, you do find again and again, right? And if you are doing a find, you may have to traverse a lot of tree for certain element multiple times. So and because its parent is always the same, can I not do some pointer update? That is, so let me first show a picture, something like, suppose this is my set. Now, and suppose I am doing a find operation on 12. Say find on 12. So what I will do, I will follow this path. I'll follow quite a few nodes until I reach 2. And of course 2 points to itself. Now while I'm doing that, can I not use this chance, because I'm anyway traversing this path, to also say, okay, well, for the next time when you find 12, directly go to 2. So instead of traversing all this, can I not directly point it to 2? So this is path compression. So instead of doing all this path, I just change its path. Okay, and because you see, I don't worry about its parent. I don't worry, okay, 12's parent is 11. I just need to know what is the ID of 12, and that's where I need to go to 2. So because I'm anyway following this path, at the end, once I find the root, I change its pointer back to root. And not only for 12, I can do that now for all the elements that were there in the path. So I can create a new tree using path compression. So where this doesn't change, but now here all this path, so 12, so 11, so I'm just putting them at the same place they were, 12, 8, 5, 10. So 5 was anyway pointing to 2, but now 8 also starts pointing to 2, and 11 also starts pointing to 2, and 12 also starts pointing to 2. What about 10? See, 10 was not in the past, so it will keep pointing to 5 that it was doing earlier. But now 12, 11 and 8 are pointing to 2 directly, and that will help later on when you are doing find for 12 or even 11 and 8. You can directly go to 2. And you see, this will reduce the time for find like anything, right? If you keep on doing this for a few times, all the long paths will go to path of length 1. Okay, and yeah, so this is your path compression. So formally what you do, so in a find operation, for each node v, that this find widgets, reset the parent pointer from v to point to the root. Okay, that's all you do. Fine. And actually, if it has been shown, yeah, we will not go into the analysis. This is quite involved. So the analysis shows that using this path compression, for a sequence of, so this is again amortized analysis, for a sequence of m operations of find, that is getting equal to n. So n is the number of nodes. Has a complexity order m log star n. Okay, now yeah, you say, okay, what is log star n? So log star n is a recursively defined function, so it's like an iterated logarithm, so you keep on applying logarithm. So what is log star n? It's recursively defined as, so in the base case, log star 1 and log star 2 are both 1, the ceiling over log n. Okay, so it's a recursive definition. So for example, if you do log star of 4, that will be 1 plus log star log 2n, so that is 2, so star 2, and log star 2 is 1, the base case, so that is 2. Okay, similarly, if you do log star 14, that will be 1 plus log star, now log 15 over the floor will give you 4, and log 4 we have log star 4 we have already found out 2, so this will be 3. Okay, but this function does not grow, it is very, very slow. So take something like log star 60,000, this will be 1 plus log star, and if you actually take the log of 60,000, so you will see this will be because 1000 is close to 2 to the power 10. So this is roughly is less than 2 to the power 16, right? So 64 is 2 to the power 6. So this is, and if you take the ceiling, it will be 60. So 1 plus log star 16, and log star 16 is 3. So this gives you 4. So log star of 60,000 just gives you 4. And actually, you can see that for any number n less than equal to 2 to the power 65536. Okay. So this is actually quite a large number for any practical purposes. Your log star n is less than equal to 5. Wow. So that means this is as good as constant. For all practical purposes. So it will not go beyond 5 for n as large as 2 to the power 65,536. Okay. So yeah. So that means if I do path compression, so that means path compression helps in achieving order m log star n plus n complexity for m finds and n unions, and which is order m plus n for any practical input. Okay, that looks very good. I have an order m plus n complexity. Okay, so yeah, so this is why the tree data structure is very, very, very interesting. I can quickly, you can also write these pseudocodes. I can also give you a quick hint about the pseudocodes. So if you, for example, if you want to do this make set, so you can do it for each element. So for each singleton element x, you do x dot parent is x and x dot size is 1. So this is very important because for union by size, the element should store the size. Okay, and this will change only during union, only for the root node. This will change. So let's see. So for union xy, now so let's assume that x and y are both the individual roots. So that will also need to do a very little change in your initial algorithm. So where you will have to say, okay, you are finding, go back and check, you are doing find x and find y. You have to store what is that. So something like a is equal to find x, the root, b is equal to find y, and then you say, okay, union, if find x is not equal to find y, or if a is not equal to b, do union of a b. Okay, that is how you can use this particular implementation. So union x, y, assume x and y are individual roots. So what you will have to now check, first of all, which one has a smaller size. So if x dot size is smaller than y dot size, what you will do, you have to change the parent pointer of x. So x dot parent is y. Okay, and size for y will change now. So y dot size is y dot size plus x dot size. Okay, else y dot size is greater than or equal to x dot size, so you say y dot parent is equal to x, and y dot size is x dot size is y dot size plus x dot size. Okay, so union is also very easy. So we are just updating the size for the root of the combined tree. Now what about find? So I have to find x, that means I have to find the root of x, and I have to also do the path compression. So I need x, so let me define another variable, that is x. So r is equal to x, and now you keep on going to its parent pointer. So while r dot parent is not equal to r, you keep on r is equal to r dot parent. Fine, and that will help you, this thing will help you find the root. Now okay, so r becomes your root. Now have another variable for x, and now try path compression. So I'm just writing it here from here. So while, so actually you write very similar thing, while z dot parent is not equal to z, you go to the next, so w is equal to z. Now you have saved z, now you say z equal to z dot parent, okay, and w dot parent is equal to r. So you have just moved the parent of each node, so on this path, so while you're following this path again from x to root, each path you have put that element as variable as w and make its parent as the root. Okay, and yeah, this step will anyway be needed for keep on going to the root. But this, so this and this you can see matches this to find the root. You are using it to go up to the root, but w is equal to z and w dot parent is equal to r is what is being used for path compression. So this is how you can implement it in with a suitable data structure to have pointers to the parent and so on. So fine. So I think, so this was a very interesting abstract data type that we have seen. So in summary, we talk about this abstract data type of disjoint set or union find, and we say that it supports the operation make set x, find of x, and union of x and y. And we tried various implementations. So this was the operational view, and we saw the implementation view, and we tried simple array, linked list, and trees. Okay, and we saw that for an algorithm that needs M finds an N union, tree based implementation works the best. So actually this M find and N union is very important. Generally for all the algorithms that use this, generally they go to this M find and N union. So you will see even in the Kruskal's algorithm, you will also need some for make set, but make set is generally n. So n make set, okay, and make set is generally order 1 for each of the implementation. So what is problem is find an union. So we saw that in the case of union was a problem in array and find was a problem in range. But yeah, so if you use tree-based implementation, generally it is close to order m plus n, and that is very good. That's what you can use for Kruskal's algorithm. Now, while doing all that, we have talked about two very interesting things. One is abstract data type, another is amortized analysis. So this you do whenever you have a sequence of n operations, and the worst case comes sometime but does not come all the time. So worst case appears once in a while, but average analysis gives a more realistic picture. Okay, so yeah, so this was about this data type. I hope this will help you to even think about how to create a new abstract data type and how to think about implementation for that. And this you will directly use in the Kruskal's algo that will be taught next. Okay then.